So today we welcome to Victor Marum from the University of Campinas, Brazil, and he will talk us about archeomagnetism in South America, database curation, reference curves, and reassessment of the geocentric axial dipole hypothesis. So Victor, anytime you want.
Okay. Okay. First of all, thank you very much for the invitation to give this presentation in MagNetZ. It's a big pleasure for me to be here. I'm a last year PhD student at University of Campinas in Brazil, and today I'm going to present our results on archeomagnetism in South America. And all researchers who are involved in this work are mentioned in this box, including my supervisors Jovan Hartmann, Felipe Terranova, and Hagayamit. What you can find in this presentation? A brief introduction, a new database for South America, some reference curves for intensity in South America, the GAD hypothesis reassessment, and some conclusions and perspectives. Starting with introduction, here we have the classical comparison between the Earth and an onion. Like an onion, Earth is composed of layers, the inner core, which is solid, the outer core, which is liquid, composed mainly with iron and nickel, the mantle, and the crust. The Ampere's law for magnetism, which is one of the Maxwell's equations, explains how the geomagnetic field is generated in the outer core. The helical movement of the electric current in the outer core, J, generates a magnetic field B, where μ0 is the magnetic permeability in the free space. So the geomagnetic field acts like a shield protecting our atmosphere from solar wind and other cosmic particles. And it's due to this shielding effect and, of course, other factors that life is possible on our planet. So, if the geomagnetic field were perfectly dipolar, I mean, if the magnetic field lines were symmetric like this image, we would have a map of intensity at the Earth's surface similar to this one, with an equatorial symmetry, stronger in the poles and weaker in the equator. But in fact, the geomagnetic field has this behavior. The lines are not symmetric with dipolar and non-dipolar components. And the intensity map at their surface has this behavior without symmetry, with a weaker field in the South Atlantic region. And this region with a weaker field is our fabulous South Atlantic anomaly. So, briefly about the South Atlantic anomaly, it is a region of the globe surface presenting a weaker field intensity. And just out of curiosity, I'm speaking now from Campinas City, which belongs to the São Paulo province, and it is located exactly in the center of the South Atlantic anomaly. And this anomaly is associated with the reversal and normal flux patches at the core mantle boundary, and some consequences of this anomaly are greater exposure to cosmic particles and solar wind, interference in satellites, communication and positioning system, and disorientation of some species which are guided by magnetic effects. And we know that the South Atlantic anomaly presents a westward drift, and its area is expanding over time. It can be observed in these plots. So, what is the GAD hypothesis? GAD acronym comes from Geocentric Axial Dipole, and this hypothesis states that the geomagnetic field is produced by a magnetic dipole at the center of the Earth and aligned with its rotation axis. These are the main GAD equations. The total field H is related to the latitude lambda by the magnetic moment m, where Re is the Earth's radius. The inclination is also related to the latitude by trigonometry, and declination is 0 degrees. We know from literature that GAD works well for timescales higher than 10,000 years, for paleogeographic and tectonic reconstructions, and for a better comprehension of the geodynamo. But GAD's accuracy may be questioned for timescales lower than 10,000 years and in region with strong non-dipolar contributions, which is the case of our incredible South Atlantic Anomaly. Well, let's move on to our work now. The first part of our results, which is composed of the new database and the reference curves for South America, is available in this paper published by our group in the beginning of this year at JGR, and it can be accessed by this link here. Starting with the database, our database is named SAGEOMAG database, the South American Geomagnetic database. All records in our database were subjected to a strong data curation and review, especially the older records. Our database comprises intensity data obtained from archeological artifacts and volcanic material, with possibility for future expansion, for example, to include sedimentary records. It comprises almost 2,000 records discriminated into site, fragment, and specimens. We also added 5 new studies after the last version of published, the Geomagia database published. And it includes statistical parameters at specimen level from the Array-Nagata diagram, such as the gap factor, the fraction of natural remanent magnetization, the quality factor, and others. And regarding the geographic distribution of the records comprised in our database, we observe a significant lack of data in the Brazilian Amazon region and in the north portion of South America, specifically in Venezuela, Suriname, Guyana, and French Guiana. There are also no reported records for Paraguay, the central and south portion of Argentina, and the extreme south of Chile. Here are some statistics about our database regarding the geographic distribution, the material type, the dating method, the paleointensity protocols, and regarding to experiments and laboratory procedures. What is important here is that the majority of data available for South America are from Peru, with almost 43% of the database. Moreover, more than half of the available data lack one of the two essential corrections for obtaining a high-quality archeintensity result, which are anisotropy and cooling rates corrections. Now the reference curves. Using data comprised in our database, we modeled the archeintensity curves based on the grid circle distance technique. That is a mathematical approach which calculates the shortest distance between 2 points on the Earth's surface, taking into account the Earth's geometry. We divide the South American territory into 3 regions based on the data distribution, and we named these curves as SARIC, South American Reference Intensity Curves, with radicals ABC to indicate which region it is referred. The radius of each region is presented here. In addition, all intensity data were reduced to the latitude of the central point of each circle using the classical daily and Legoff equation, where F real is the real intensity of each record, lat real is the real latitude of each record, lat central is the latitude of the center of the circle, and F reduced is the new corrected or reduced intensity value for each record. In these plots that show the quantity of data at the sea level versus time for each of the three regions, it is observed that there is also a large temporal gap for South America, especially in region B, which contains archeomagnetic records referring to only the last 500 years. So the archeointensity curves were generated using a robust bootstrap algorithm following the work of Thibault and Gallet, 2010. This method involves a iterative, curated least square with Hubble weights and outputs a continuous master curve with statistical confidence intervals. To conduct the bootstrapping, first we input intensity, intensity errors, age, and age errors. Then we define the knot sequence. After we proceed to the lambda selection. Lambda is the regularization parameter which controls how much the algorithm trusts on data. So, for example, the higher the lambda, the less the algorithm trusts the input data. Finally, the algorithm models the archeintensity curves with a special treatment for outliers, minimizing their effects, and the inverse problem is written in terms of the B-splines design matrix A, the weight diagonal matrix W, and the regularization matrix T. So first, we introduce the archeintensity curves for region A, where we applied different quality filters and a constant regularization of 10 to 6. The blue curves represent the SAGEOMAG, which were plotted with some traditional models in literature for comparison. The shaded function is the probability density function, and the red circles indicate the outliers automatically detected by the bootstrap algorithm. The scenarios in which we performed the modeling were regarding the presence or not of anisotropy and or cooling rates corrections, and also regarding a minimum of 2 or 3 specimens per site and a combination of several filters regarding the laboratory correction and the minimum of specimen per site. Unfortunately, the time is short for details, but what matter most here is the presence of some temporal gaps and changes in the curve's behavior as the most stringent filters are applied. For region B, we modeled the curves considering the different recording levels, site, fragment, and specimen in the ROS, and testing two values for lambda, 10 to 3 and 10 to -1 in the columns, and the SAGEOMAG B curves become significantly more sensitive to geomagnetic fluctuations when modeled with specimen level data. So even a weaker regularization, even using 10 to -1, it produces more consistent curves with lower errors when applied to fragment and specimen level data. And SAGEOMAG B curves were able to capture some fluctuations of the field that are not captured by the global models used for comparison. Finally, for region C, we tested different temporal intervals, a longer, an intermediate, and a shorter interval. And in the last one, we also applied all filters that were applied in region A. The modeled curves could also capture some local geomagnetic nuance that global models tend to smooth or overlook. Now, let's get into the GAD hypothesis reassessment. To evaluate the GAD hypothesis, we conducted a synthetic sampling. First, we selected 5 locations for a preliminary test, 2 fixed points, Paris and São Paulo, and 3 time-dependent points, minimum, maximum, and min PI. PI is the very elegant PSV index proposed by Panowska and Constable 2017, and this metric represents the average deviation from a gate field. PI is calculated with intensity, directional, and latitude information of a point in space and time. And the most interesting aspect of PI is that it doesn't need a model to be calculated. And here are the maps plotted with the chaos model presenting the intensity at the Earth's surface and the values of PI in 2020, in addition to the 5 locations chosen for this preliminary analysis: Paris, São Paulo, minimum, maximum, and mean PI. Okay, so we conducted a Monte Carlo experiment for ensuring statistical robustness using data from chaos model for 2020. And this experiment aims to evaluate these 3 fundamental parameters: number of random sites, number of independent clusters, and radius. Here is a simple illustration of the experiment we performed, where F half is the intensity of one of the 5 locations of interest, and F real is the absolute intensity of a synthetic site inside the region delimited by R. So all configurations were repeated 100 times by varying these parameters here inside these intervals. And we estimate the coefficient of variation delta F, which computes the deviation between F real and F reference normalized by F reference. After we proceed to the test of several approaches, including some latitude correction equation for estimating the variation of delta F with R. For the second analysis, we used the results from the COVOBS model and considered 3 epochs covered by this model, which are 1840, 1930, and 2020. We investigated the variation of delta F with R with a fixed number of sites and fixed number of clusters for each experiment. And we tested 5 different latitude correction equation and approaches. The first approach is using the absolute values of F real without applying any kind of correction for latitude. In the second scenario, we reduced the intensities F real to the same latitude as F reference using the traditional equation proposed by Daly and Legoff, which is the GAD approximation, where lambda center is the latitude of the reference point, lambda real is the latitude of each site, F real is the absolute intensity of each site, and phi is the longitude. Okay, in the third scenario, we derived the equation of intensity considering both G10 and G20, where big G20 appearing here is the ratio between G20 and G10. In the fourth scenario, we also derived the equation of intensity, but now considering G10, G20, and G30, where big G30 appearing here is the ratio between G30 and G10. And all of these 6 big symbols here are expressed as a function of latitude and big G20. Finally, the last scenario, we tested the eccentric dipole approximation. The idea here is to compute the intensity at a point P in the Earth's surface using a system of coordinates regarding the displaced dipole. We have this main expression to calculate the intensity F at a point P for a given time, written in terms of r prime and lambda prime, which are the coordinates of P in the eccentric dipole model. And the main challenge here is to calculate r prime. For that, we have several equations to change coordinates from the center dipole model to the eccentric dipole model. And the elegance of this formulation is that all the main variables are written only in terms of the Gauss coefficients up to degree n order 2. Now the results. The first results consisted of investigating the behavior of delta F as a function of the three fundamental parameters I told before. And the idea is to define convenient number of sites and number of clusters for further investigating the accuracy of the 5 scenarios for estimating the behavior of delta F with R. Okay, here are the results for the Monte Carlo experiment using the chaos model for 2020. Initially, we evaluate here the behavior of delta F with the two parameters, number of clusters and number of sites, in two different scenarios without latitude correction, no correction, and using the gate hypothesis. In the first row, we kept a constant r equals to 500 kilometers and varied the number of sites into 5, 10, and 100. In the second row, we also kept a constant radius of 500 kilometers and varied the number of clusters to 1, 10, and 100 for both scenarios. So we assume that GAD works when delta F is lower compared to the scenario with no correction. So basically, GAD works in this year for this model for Paris and minimum PI and min PI, and GAD fails for São Paulo and maximum PI. We could also see here that the number of sites equals to 100 and a number of clusters also equals to 100 is enough to stabilize the metric delta F. Here are the results for behavior of delta F with respect to the radius R. We adopted number of clusters equals to 1 and varied the number of sites in 5, 10, and 100. Also in two different scenarios without latitude correction and using GAD. In these plots, we don't reach a stabilization of the error with the increment of R. And an interesting observation here is that in this statistically robust experiment, we already see an error of 5% within a 1,000 kilometer radius, for example. 5% or even more if we consider São Paulo. Here we have the test of the 5 approaches for Paris and São Paulo for the 3 epochs, 1840, 1930, and 2020, with fixed number of sites and fixed number of clusters. The GAD, the red curve, works for Paris in the 2 last years and fails for São Paulo. GAD is inconclusive for Paris in 1840, as GAD and the no correction curves, the black and the red ones are overlapped. So it's inconclusive. We also did the same analysis for other 8 points, minimum PI, maximum PI, min PI, and cities such as Guadalajara, Tokyo, Cape Town, Perth, and Ushuaia. I'm not gonna show you this analysis now. We don't have time for that, but you have to believe me that we did this analysis, but I can show in the end of the presentation. So our preliminary results allow the proposal of this plot, which correlates PI and the metric D, calculated as a mean of the ratio between delta F with GAD and delta F without correction for each R. In green circles, we have the points where GAD works. In red circles, we have the points where GAD fails. And in gray circles, the points where it's inconclusive. Each symbol represents one of the 10 locations of interest, and the colors of the symbols correspond to the 3 different epochs. What you can see here from this plot is an indicative showing that GAD works when PI is lower than approximately 0.08. Higher than this value, GAD can work or fail. But we thought that we should investigate more, and we decided to go further by performing the same analysis not only for 10 points, but for a regular grid on the globe. And we did the same analysis for all of these 100 points. And what we see here with all the 100 points for three epochs is that we cannot state that gate hypothesis works or fail as a function of only pi. We are not able to find a minimum or a maximum value for pi, which is decisive to indicate if gate works or fails. And now we are looking for a possible correlation between the gate accuracy and another parameter not dependent on model results. So for closing this presentation, I bring here some conclusions and perspectives. These results support the reconstruction of South American geomagnetic field through an organized database and bootstrap modeling. Our database improves the organization and availability of South American records. This study identifies spatial and temporal gaps in the data distribution of South America, guiding future sampling efforts across this territory. Quality filters affect the temporal distribution and the shape of the curves, and the spheric resolution may be improved at lower hierarchical level when combined with weaker regularization. We also aim to investigate the efficiency of the gate hypothesis in different points of the globe for relocating archeomagnetic data. We observe that even in a statistically robust experiment, an error of approximately 5% is propagated. We are looking for a robust metric that can be related to PI to indicate whether gate works at a given point in time and space. And these preliminary results can contribute to the modeling of local time series and to the construction of more robust model. In parallel, we are now working the construction of an archeomagnetic regional field model for South America based on the revised spherical Kepler harmonics analysis and Bayesian inversion with column filter in collaboration with Dr. Maximilian Schanner from GFZ in Potsdam. So I finish here. Thank you very much for your attention. It will be a pleasure for me to discuss these results with you. Thank you very much.
Well, thank you. Thank you, Victor. Very nice talk. So we will open the microphone for questions, or you can type them if you want. Usually it takes a few seconds for people to give a step forward. Otherwise, I will make a question. Okay, nobody raises their hand yet, so I will do mine. So a very simple question is how do you define the site level data for archeomagnetic data? So what is
Question.
site for you?
Yes, for definition, we adopt site level data as a point in time and space, a value of intensity or directional in time and space. I can show you here in support slides. Here, yes.
Good. So you have.
Okay, so uh, regarding material preparation sampling, the most appropriate manner to do the proposal of a high quality archeintensity value is to go to the site, to extract fragments, to divide this fragment into specimen, and these specimens are subjected to the laboratory experiments, and then an average is created at a fragment level, and then an average at a site level. So I think it's the best way for ensuring statistically robustness analysis. And so
Okay.
site level data is, uh, I don't know if I answered your question.
Maybe. I mean, I don't have experience in archeomagnetism, so aside for you is just the geomagnetic their geological site. So you get one
Yes,
data for one archeological site, right?
Yes, and a
Okay.
robust intensity data at site level for me has to be subject to this average. Yeah.
Okay. Okay, thank you. Someone else?
Yes, me, please, Miriam. Hello,
Go
nice
ahead.
to meet you. Good talk. I would like you to notice that, in my opinion, the main problem in South America is that a huge part of the data are not very robust because they were obtained from pottery and they are not corrected for the theorem anisotropy. And this is much more important than, for example, your 5% for relocation, because in some cases we can change the intensity value between, I don't know, 100 to 50, things like that. So I think it is very important to really select the data that are correct for this kind of studies. But very nice work.
Thank you. Yes, just for yes, I totally agree. The big majority of data, mainly the older records from the 60s, 70s, so they are lacking this kind of corrections, and it, of course, should be filtered and uh, receiving another kind of treatment, because we also cannot disconsider them because we have few data. We have to
Yes,
give a special treatment to them.
or we need to obtain more robust data, yes, because there are some data that are clearly not real. So
Yes.
it is important to discard, in my opinion, to construct the curves or the models. But for the moment, we have not so many data. So
Yes.
okay, thank you very much. Congratulations.
Thank you.
Marina, go ahead.
Thank you, Victor, for this nice talk. And I was curious about do you know if there's some ongoing project on your institution to get more data in South America?
Mhm. Hello, Marina. Thank you for the question. Yes, yes, we have a project here, a big project here in our institute, and one important part of this project is related to these campaigns across South America for collecting this material and to provide new archeomagnetic information about them. Yes, it's really important, and I think it will help the construction of models and the understanding of the behavior with more details in the South America.
Thank you.
Go ahead, Sanja.
Sanya, yes, thank you.
Sania, sorry.
That's fine. Thank you, Victor, for the nice talk. I have a question regarding the GAD hypothesis and the new metrics maybe you're looking. Do you have anything in mind or which direction you're going with the new metrics?
The metric you mean the
Like the PSV index, you said you didn't work on distinguish, right?
just a moment here.
No, towards the end. When you try to distinguish when the hypothesis. It was one of the last slides.
Okay. Yes. Sorry, could you repeat your question, Sanya, please?
So on the next slide here, it kind of you can see the corner and you can distinguish, but then when you did the global search, it was inconclusive. So
Yeah.
we probably need another metrics to relate this to say okay when it works, when it doesn't work. what do you have in mind? Like, for example, VGP dispersion, or did you check some only VGP source or something else completely?
It's a good question, Sanya. Thank you for the question. Yes, we are investigating now what is a better metric for trying to distinguish this correlation if gate works or fails. Our idea is to try to modify the PSV index for adding or removing some parameters to see uh, what's going to be the outputs. Yeah. So this is our first step. Try to change this formulation, and if it doesn't work, uh, I confess we don't know what to do. We have to investigate in other parameters like combination between declination, inclination, and intensity with latitude and do something like this. Yes, hopefully we can find this expression.
Yeah, no, definitely. I mean, we propose it, but I don't think it's ideal, and that was I think that's how the science goes. You improve it on the way. Yes, thank you.
Yes.
There is another question from Yutaka.
Hi, Victor.
Hello.
Thank you for presentation. We met at Vienna 2 months ago, and I have
Yes.
one question. Please, could you go back to the slide of the archeointensity curves?
For region A.
Yeah.
Mhm.
Yeah. For example, for all panels it shows the very scattered archeintensity data. For example, around 500 BCE.
500 BC, like here.
Yeah, low intensity and low intensity around 10 or 20, and intermediate archeintensity around 40 or something. We can observe. So yeah, but your model is going along the lower archeintensity. So what do you think about these scatter and your model is going to the lower region of the archeintensity? What do you think?
It's a very good question. Thank you for the question. I think it's a similar discussion we had in Vienna this year, and the algorithm that we used try to capture this low intensity, and this capture was not observed by the global models, and I think this can it's a feature. It's only a feature captured by our model. I think it's too early to have some decisive conclusion for that. But it's a trial for adjusting, in my view.
Uh,
And if you see here, the global models don't follow this trend.
yeah. What is the cause of these differences?
The colors.
What is reason of these
The
differences between your model and the previous global model? What is the reason of the difference of models?
Yes, it's a good question. Global models involves data from all the globe, and probably they didn't follow this trend for some reasons, uh, probably because of the regularization they are using, or the some temporal or spatial gaps. I don't know. I don't know exactly.
Okay, thank you.
You're
Thank you
welcome.
so much.
Any other question? Okay, if there's no more questions, we thank again, Victor. Thank you so much.
Thank you very much for this opportunity. It's a pleasure.
Great talk.